So yeah, Matt asked me to talk a little bit about my library, which I possibly misnamed pre-cog. It was originally intended to be kind of a set of examples and a couple blocks to use for a tutorial at DieSpan. That's the pre-cog. It's not quite a cognitive radio library, but might be something you could build a cognitive library from. So basically what it is a library built on top of Josh's gr-extras work. So we do a lot with message passing and those features. All of the blocks are written in Python. And the other thing I was kind of trying to show off is kind of these, some of these newish features that we've added. You guys are all familiar with the time bursting and metadata and tags and all those. But we also added the time commands for tuning and GPIO and so forth and so on. But we really didn't have any examples showing how to use those. So I wanted to create this set of blocks that could have this kind of FHSS implementation and do the time bursting. I'm getting there. And do the time bursting and time tunes. So we can do things like frequency hopping and TDMA and make it easier for people to kind of play around with that. So from a high level, I mean, you guys know what PMTs are, so I won't go over that. Josh, correct me if any of this is incorrect, but basically the blob is fairly simple, and that's why I chose to use it. In these flow drafts that I'm going to show you, I wanted to have the capability to pass around these raw frames of data and kind of...
We collectively decided yesterday apparently to call them datagrams.
I don't know if we decided. We decided blobs wasn't a good name. But
I mean, in the other room there was some RPM discussion.
Oh, we call them datagrams now?
Datagrams
data units, PDUs,
Datagrams are a loaded
NDUs.
term,
Yeah.
especially if you're using...
No, a datagram is it's IP datagram.
Right,
It's
but it's data units.
Ethernet frames,
Yeah.
so
But datagrams are one of them.
we need some, yeah. I
Actually,
wouldn't worry about it too much.
I think
I would go with blob for the duration of this.
For the duration of this presentation, it's a blob.
blobs are no more crude than saying chunks to symbols.
Okay, fair enough. Basically, it amounts to a PMT, and its value is a byte count and a pointer, right, Josh?
Yeah.
So effectively, you can move data around somewhat efficiently, and if you just do want to pass around those raw bytes, it's useful. So going down, here's an example of if you wanted to connect two TCP/IP sockets and have them exchange data between the two. This is what it would look in GNU Radio flow graph, for example. This is a simple radio where it goes a TCP to TCP socket, right into the framer to GMSKD mod. But kind of what I built on top of that was a couple blocks that would do some, you might call it MAC layer functionality. So doing ARQ and radio addressing. There are a couple PHY implementations, one for TDMA, one for frequency hopping, one that's more like a kind of a random access, half duplex kind of thing. And all those are somewhat interchangeable and can be used with those upper level MAC implementations. So what you get is a flow graph that looks like this. And kind of a cool thing that I noticed in this, and I don't think the implementation is really that good, to be honest, the way I've done things in Python. People probably do it a lot more efficiently and speed things up. But the cool thing I did notice is that when I took this to DieSpan, I took this to places where people had no exposure to GNU Radio whatsoever. They were able to kind of build up their own custom bursty packet radios and do all kinds of different data sources and syncs. So sometimes we get a lot of support questions for 20-watt PHYs because people don't know how to properly set it up. And those problems would still exist with this to some degree. But in terms of being able to modify it, now you're able to kind of do it in the graphical domain instead of having to jump into that piece of code as your very first project. So this is a simple example of, again, connecting a TCP/IP socket so users can get data in and out, but connecting that to a simple MAC layer block that does radio addressing. That's where the ARQ is implemented. And in between that, you actually see this formatter, and that's really just kind of a shortcut I used. Ultimately, this kind of formatting would be available through an API, kind of like packet utils in a way. But this says, okay, I'm going to take this data stream coming from this TCP/IP socket. I'm going to encode it so it goes to the radio with address 86. I will use ARQ on the stream because that is optional, and it goes through here. And this is kind of what the ultimate path looks like. User enters data with netcat or some other way to get TCP/IP datagrams into this. Goes through the formatter, goes out the MAC. He puts a header around it with the address and some control bits that tell it what the ARQ is doing and what protocol format he's using. Goes out the radio port, right? So this is just again a blob of data with a header on it. Goes into the radio top block, which I'll show in more detail in a second. Over the air, and kind of the opposite process happens. And of course, this is mod, demod, mod, demod, and the usurp interface. And the same over here. Goes over the air, gets decoded, DCRC, and comes out as a blob. This guy looks at the header and says, "Oh, this was a packet intended for me. I'm going to actually look at it. If it asks for an ARQ, I'm going to send an ACK back out, my output port." And if it was the user data protocol, I'm going to pass it along to the socket. So fairly straightforward implementation, but again, fairly modular, so you can do different things. If you don't want it to be just a TCP/IP socket, and you want it to replicate what tunnel.py was doing, but have this ARQ in there, all you have to do is add this tune tap interface. And in terms of the flow graph, it operates the same way, but now you have a tune tap interface to get bytes in and out instead of just raw bytes through TCP/IP. So effectively, this implements what all of the code in tunnel.py does, only it's graphically, it has ARQ, so you don't have to use TCP/IP as your ARQ mechanism, because it's pretty bad at that. And then, it's fairly modular, so if you wanted to take a different physical implementation, or even change things around, it's fairly easy to do that. So I got a reasonable response out of people using it. Again, a lot of them had very little experience, so it was a good test. And then I'll show you some real demos, but it's easy to add multiple data sources and change the type. So this is if you can't decide if you like tunnel.py or the other way. You can have both and use what I call a virtual channel mux and demux, and what that adds is another byte in the header that says, okay, this is the stream. It's basically like I don't know what the correct terminology would be here, a virtual channel, so you can multiplex all these different data sources on it, and it doesn't just have to be raw data from a socket. You can actually implement higher level protocols in other blocks, like for quality of service or link management. I'm presently working on one that interacts with the white space database and pulls channels out, and we'll do kind of the audio negotiation for white space radio implementation. But he'll sit on top of this, separate possibly from the user data path, and he'll exchange data over the air, but we'll also have his control ports connected to the radio and the MAC, so he can adjust parameters based on what channel he wants to use, what he's allowed to use, and things like that. And here's just another example. You could do something like, I kind of have this running. You can put encoded audio into this and get it in or out, and video or whatever else you can think of. This is kind of one of the simpler physical layer implementations, just GMSK, mod and demod. We are using burst tagging here. So it is half duplex, or you can run it as full duplex as well. And it's got these control ports to the RPC blocks. Some other physical layer implementations, frequency hopping and TDMA. And yeah, just an overview of the frame structure. This isn't really that interesting. Just shows you kind of how we're packing things in, what fields we're using to kind of make sense of it all. Some of the Python code. So I can hop over here. Do you guys have any questions as I'm Okay, so, you know, one of the simpler examples I can show you here, again, is that one I showed you that's doing just the kind of one virtual channel TCP/IP connection. So I can run this flow graph, but since I'm running two different instances, I need to pass a few more command line parameters in. So this is actually making two different ports. I have two different USRPs I'm talking to. I'm using the MIMO cable to talk to both, but not the synchronization features of the cable. I can start these two up pretty easy. Open up a netcat, and now I can just send these two messages back and forth to these two terminals. So these are, you know, each of these netcat instances are connecting to two separate instances of the radio. That's kind of like the out-of-the-box example of how you might use this, is just to send data back and forth. And that could be any type of data that is sent over TCP/IP via socket. So just as a more extensive example of how you can manipulate kind of the application layer of it, again, this is showing how you can get multiple virtual streams in and out of the system. And again, we're using multiple virtual channel formatters, so practically, you know, you could assign each stream to a different destination address, and you can make some streams use AirQ for kind of guaranteed delivery, but make some of the maybe higher rate streaming data not use AirQ. And you know, again, this block is kind of makes it a little bit hackish. Ultimately, that would be exposed via an API that says, okay, I'm going to make a packet for this address and these parameters and send it out as a blob instead of having to go through this. But visually, that helps you understand how we're kind of assembling things. And what he does is he actually basically puts some metadata in the key, and the MAC block takes that information and says, okay, this is what the key looks like. So I'm going to process this block of data this way, and I'm going to, you know, put the header on accordingly. So this example here, we are simultaneously sending a compressed audio stream. We're doing that text message thing with AirQ via the TCP/IP socket, and we're also sending a kind of low-rate beacon message. Okay, and they all get merged into one data stream. It goes into Simple MAC, and on the opposite end, you know, once the receiver takes that header off, he puts it out to the virtual channel demux, and demuxes it out to the corresponding endpoint. So I can show that working here. And in this case, I'm not actually using an audio card because that would create some just contention issues since I'm running multiple instances in one computer. But I am showing the FFT, and I'm actually outputting the received audio to a WAV file. It looks a little goofy. I think that's because of the compression I'm using, and that's the codec 2 compression. So you can see that coming through and going to the audio FFT. At the same time, that beacon message is going to a message to the standard out block that I made.
What's your frequency of your main tone?
1 kilohertz.
Okay, so codec 2 is likely,
Okay.
it's trying to figure that this is voice,
Right.
and it
yeah.
knows that nobody's main tone is at 1 kilohertz, so it's assuming that you're actually talking at 330 hertz.
Yeah, I know that those things don't typically operate very well on that tone.
Yeah, so that's fine. That's,
Yeah, anyway, so while that audio data is going through the system, okay, we also have these beacon messages coming through periodically. And just to show you the data path, okay, the beacon messages come through and just go right to this block that outputs it to the standard out of the flow graph itself. Okay, and those are both non-AirQ paths. But at the same time, we're also running the TCP/IP socket with AirQ. So if this one drops a message, it actually resends it. But you can see that this MAC layer is kind of handling all these different streams, and it's very easy to plug in different data sources and make this radio send other things besides, you know, just TCP/IP data. And again, you can put that tune tap in it, and essentially you've got tunnel.py in a graphical world. Yeah, so all those issues of frequency offsets and people just not knowing, I think you just have to educate to get around those. But being able to modify it and make it do a little bit more what you want to do, it's a lot more modular.
Right, and having the link layer retransmissions is very important.
Yeah.
So
Right.
that's huge. Tunnel.py never had that. It relied on TCP for the retransmissions, and TCP for retransmissions is not
Right.
the way to do it.
Yeah, and the particular implementation, ARQ implementation, it's stop and wait. So it's not good, but it's just to get it started. More, it's actually wrote a sliding window implementation that I'm going to merge. And that's a lot more helpful when you're doing things like TDMA and frequency hopping, where you've kind of got this turnaround time just by the nature of your slot assignment, and that kind of sets your timeout for your stop and wait ARQ. So anyway, that's kind of like 3 different data paths going on at once, and you can have an arbitrary size. And again, the cool thing is I can put a whole separate higher layer protocol to kind of set the behavior of my radio and make that pretty much completely independent, as long as I've properly defined my control port functionality between all of these blocks. And I did that in part with the next example, which is a frequency hopping implementation. If I can get these guys closed. So the frequency hopping implementation can be temperamental from time to time. But just to give you an idea of what's under the hood there, these are blocks that are written in Python. And basically the way they're working is they're looking at the received sample stream from the USRP and determining the outside world time, so to speak, the time of the USRP. And once he knows that, he knows, okay, I have to schedule a tune request or a burst so far in advance of my next transmission time. So he keeps track of that time and then issues a time burst with tags, but he also uses a PMT RPC block to send a timed tune command to the USRP. So essentially, the time comes up, he says, okay, I'm going to tune. I'm going to set the tune for this time, sometime in the future, and then out the data port on the data plane, he puts tags in with the data, and he sends out all the frames he has in the queue. If there are no frames in the queue, he'll actually put in like a preamble frame, so the receiving end can kind of maintain synchronization on the frequency hopping. And then on the receiving end, there's kind of a state machine in there that looks for the reception of a frame, and once he sees that, he kind of starts hopping synchronously. And right now, we just hand the frequency lists to these blocks as just comma delimited floats. I mean, you could generate a pseudo-random pattern and just hand that to them. And ultimately, eventually there will be control ports, so you can. And when I say control port, that's different. That's your control port. So. You know what I mean, but so you can perhaps change all of those things during runtime. But again, that goes out to the USRP. And there's also a TDMA implementation that looks very similar to this. But anyway, the cool thing is we just take that block and we plug it in as the physical layer right on that other flow graph that I showed you. Keep the same MAC layer. And everything else looks fairly similar. So I can go run that, and there's not a lot of visual to this, so you just have to bear with me. And to be honest, it's not hopping incredibly fast. I haven't really looked for the optimal configuration for this presentation. But so you didn't see it. Let me actually restart one of these. So you see that this guy lost synchronization, and he said, okay, I'm initializing channel 0, I'm going to start searching. Okay, so I'm going to turn this other radio back on and start that frequency hopping transmission, and I come back over to this one. You see he detected a frame on that particular frequency and then started hopping along with the transmitter. So there's actually, there's both a receive and transmit chain on each of these, so it's full duplex frequency hopping. And just like the other one, I can come in here and send some text messages back and forth between the two. So I pulled out that physical layer, my MAC layer, stayed consistent. So all those things I designed at the application layer can still function as they have before. So anyway, that's the basic gist of it. Gave us a way to.
No, what
Spectrum
frequency are you
video.
on?
Sorry.
Spectrum video.
Sorry.
What frequency are you transmitting around?
Probably 915.
We want to see a waterfall spectrum can pull it out.
So when I'm not sending data, it is sending those preamble frames, but they're very, very short.
That's what I was.
I do have a video somewhere around here of where I intentionally stretched out those preamble frames. Running auto setup. So this is where I had made the preamble bursts very long. And I gave it a sequence that was doing this kind of random hopping, then did kind of a chirp across this.
Okay, so the
You've got some things here, I think, from IQ balance and whatnot. But
Yeah, you see a mirroring.
right.